Hey guys, there's just a few problems I wanted to do for you. Related rates, this is number 25 from page 155. Sorry, all my kids are home too. Alright, a ladder 25 feet long is leaning against the wall of a house. The base of the ladder is pulled away from the wall at a rate of 2 feet per second. So related rates. What's given? Determine a geometric relationship. Derive that equation. So geometric equation. Derive that equation with respect to time, and then solve the problem. So let's look at part A. A ladder 25 feet long is leaning against the wall of a house. The base of the ladder is pulled away at a rate of 2 feet per second. So that's the given information. How fast is the top of the ladder moving down the wall when its base is 7 feet? We're going to just look at 7 feet from the house. So at the moment that the base is 7 feet from the house, we want to know what's this rate of change. So we'll call this rate of change of the ladder with respect to time. Oops. Alright, so what would be the geometric relationship to relate the three sides? That would be our Pythagorean theorem. A squared plus b squared equals c squared. We're going to derive this equation with respect to time. 2a times dA dt, and this is where our implicit comes in, plus 2b times dB dt equals 2c times dC dt. Okay, all the 2's will cancel each other out, and now let's start filling in our information. So A and B just represent the side lengths. I know that when the ladder is 7 feet from the house, it's moving away at a rate of 2 feet per second. I'm looking for this rate. And the length of the ladder is 25 feet, but we know its rate of change is 0. Okay? The length of the ladder isn't changing at all. So we still need, what is this side length? That we're calling B in the equation. Well, let's go back to the geometric relationship. B squared plus 7 squared equals radius, or hypotenuse squared. So using the Pythagorean theorem, we would get 24 as this side length at the exact moment when the ladder is 7 feet from the house. So we would plug 24 in here. Now let's solve this for the rate of change of the ladder. This gives me 0, so we would subtract 14 from both sides and then divide by 24. Both of these reduce. So negative 7/12 would be the rate of change of the ladder. It makes sense that the rate's negative because the ladder's sliding down the wall. The length is getting shorter, so the rate would be negative.
What is this, Mom?
Say hi to my students.
Hi. Hi.
Alright, now let me finish, okay?
What is that board?
Alright, now let's look at B. Consider the triangle formed by the side of the house, the ladder, and the ground. Find the rate at which the area of the triangle is changing when the base of the ladder is 7 feet from the wall. Okay, so at the moment this is 7 feet from the wall. We know the length of the ladder isn't changing from 25 feet. From the previous problem, we found this length to be 24. We know this moves away at a rate of 2 feet per second. That's given. And we know the ladder slides down the wall at a rate of negative 7/12 feet per second. That's what we found from part A. So this one sets it up for us. Find the rate at which the area of the triangle is changing. So we know area is 1/2 base times height. That's our geometric relationship. Derive this with respect to time. We do need product rule here. First times the derivative of the second plus second times the derivative of the first. Alright, we'll call this base and we'll call this height.
Mom, I want to say hi.
Go ahead, buddy.
Resend that.
Say hi to everybody, then go away.
Hi.
Okay, now be quiet.
Hi.
Alright, so 1/2. Base is 7. Rate of change of this length was -7/12. The height, we found that to be 24. And we were given that the rate of change of B was 2. Alright, so dA dt, 1/2, -49/12, plus 48. And you can evaluate that. So the test is non-calculator. So just evaluate that, get an answer. Alright, and lastly, part C, find the rate at which the angle...
Hi. Mom, can I say hi?
Find the rate at which the angle between the ladder and the wall of the house. Ladder and the wall of the house is changing when the base of the ladder is 7 feet from the wall. Alright, go ahead, bud.
Hi.
Sorry, guys. Alright, so again, we know all of this information from part A. Okay, so based on the given information, I can use one of 3 relationships. I know tangent of theta is opposite side over adjacent side. Cosine of theta is adjacent side over hypotenuse. And the sine of theta is opposite side over hypotenuse. So these are my geometric relationships. I don't want to use tangent. And the reason I don't want to use tangent, the opposite and adjacent side are both changing. So we would have to use quotient rule to derive them. So let's look at the cosine. Cosine of theta is the adjacent side, which is, I'll call A for adjacent, over the hypotenuse. Now we have talked about this. You can look in your notes. This rate of change is 0. We know that the length of the ladder isn't changing at all. So I can substitute that value in before I take the derivative. I can't plug in 7 yet because that rate, the length of that side is changing. Let's derive it with respect to time. Derivative of cosine, negative sine of theta times d theta dt. Dividing by 25, that just puts 1/25 as a coefficient times the rate of change of A. Alright, so we're going to call this A. We're looking for d theta dt, the rate of change of the angle. I have 1/25 times 7. Oops. That's not 7, that's the length of the side. So the rate of change of that length is 2. Now we got to work on the sine of theta. Sine of theta, now we can go back to the triangle with the information filled in. Sine of theta is the opposite side over the hypotenuse. So that's what I'm going to plug in. Negative sine of theta. So solving this for d theta dt, I have 2/25 times 25 over -24, multiplying by the reciprocal from the left. So I get -1/12, and that would be radians per second. Alright, implicit differentiation. So we used that already on the 3 previous problems, deriving with respect to time. Every time, whenever you derive and the variables don't match, you need that implicit step. So deriving this, 2x plus 2y times dy dt. Derivative of 25 is 0. Solving for dy dt. Subtract 2x from both sides. Oh, I don't know why I'm doing dy dt, because that was the previous problem. Dy dx. Dividing by 2y, and then we can just cancel out those 2's. So this would be the derivative of that function with respect to x. Okay, last problem. Use a left Riemann sum with subintervals indicated by the data in the table to approximate this definite integral. Alright, excuse me, we can't use this relationship here because the width of our intervals are not equally spaced. So let's look at the data given. We have intervals from 0 to 2, and then we have information from 2 to 5, then we have information from 5 to 9, and then we have information from 9 to 10. A Riemann sum is an approximation using rectangles. What?
Put some more words into my classroom.
Okay. So we know the area of a rectangle is length times width. So the width of this interval would be 2 units. The width of this interval would be 3 units. This width is 4, and then that width is 10. That's why the delta x won't work. We can't just do 10 minus 0 divided by 4 because we're not given appropriate data on equal intervals. All right, because it's a left Riemann sum, the leftmost point on each of the intervals is where our heights would come from. So our width and our length would come from h of 0 on that interval, h of 2 there, h of 5, and then h of 9. All right, so length times width. So the first interval, width of 2, and the height comes from h of 0, which from the table is 66. My next interval has a width of 3. I get the y value, the height, the length of the rectangle, whatever we want to call it, from h of 2 on the chart. My next interval has a width of 4 units. h of 5 is 52. And then my last interval has a width of 1. And the y value, the height of the rectangle, comes from h of 9. Again, non-calculator, so you guys can approximate, you can evaluate this to approximate the integral. And again, what does that represent? The area under this curve h of t between 0 and 10. Oops. Okay, so those are the examples. With those examples and the multiple choice that we did in class, which I did post to the solutions to Edmodo, I would feel you're prepared. There's the format of the midterm. Again, email me directly if you have any additional problems, questions, concerns. mainlandregional.net. And I will be available tomorrow morning, Thursday, by 7:30. If you guys, either mods, want to pop in for some questions. Okay, have a good day.